Hi, my name is Reagan, and my partners are Will and Min, and this is our presentation 3 on Chapter 2, Manifestation of Uniform Random Numbers. Section 2.1, Linear Congruential Generators. A linear congruential generator is an algorithm that results in a sequence of pseudo-randomized numbers calculated with a discontinuous piecewise linear equation. They are known as, or they are one of the most recognized pseudo-random number generator algorithms, and they are fairly basic and easy to understand. In the picture to the left, you see the basic layout of one. Rn plus 1 equals A times Rn plus C with a mod M, where Ro is a seed, R1, 2, or 3, and so on are the random numbers, and ACM are the constraints. So just a little more on these. Based on what one chooses for the values of A, C, and M, the generator produces a uniform distribution of integers from 0 to m minus 1. LCG numbers have poor quality and are not independent like true random numbers are. However, they can still be used for a lot of tasks and are very helpful. However, if someone does know Rn plus 1, then they could, or if they know Rn, then they could predict Rn plus 1 and determine the ultimate sequence, so they could kind of back into the generated list of numbers to determine what they were, so they truly wouldn't be random in the end.
Hi, I'm Ming Chen, and I will talk about the mixed linear congruential generators. So the mixed linear congruential generators is another version of the linear congruential generator. So basically, when we call mixed linear is basically by using both the multiple by A and addition by C. When C is bigger than 0, that's when we call the mixed linear congruential generators. And also this generator has to follow all the rule of the linear congruential generator, which are C and M are related prime. A minus 1 is the multiple of Q for every prime factor Q of M. A minus 1 is the multiple of 4 if M is. And an example of the mixed linear congruential generators is when A equal 9, C is 3, which is bigger than 0, and the M is 2 over 4, which is 2 times 4, which is 8. So yeah, this is a basic characteristic of the mixed linear congruential generators. It's the same with linear congruential generator, but by having C bigger than 0, it's called mixed linear congruential generator.
I will now be going over section 2.1.2, multiplicative linear congruential generators. Recall the equation for linear congruential generators is x of I equals A x of I minus j plus C mod m. The parameters are A multiplier, x naught seed, C increment, and m modulus. In the case of multiplicative linear congruential generators, C is equal to 0. So therefore, you are left with x of I equals A x of I minus j mod m. Now, multiplicative linear congruential generators, or MCGs, can also be referred to as Lamer random number generators. In the case of C equals 0, x of I minus j cannot be equal to 0, else the sequence of generated numbers would just be a long list of zeros. MCGs are similar to linear congruential generators, or LCGs. However, your A and M values are more confined as to what they can be. X naught is also more confined as to what it can be, and it must be prime in relation to M. And the greatest common divisor is 0. A, your multiplier, must be a primitive root modulo M, and M must be a prime number. Now, why are they more confined as to what they can be? The answer lies in A modulo M. So if we recall, A is the dividend and M is the divisor, and A modulo M gives the remainder of Euclidean division A by M. And that is how these numbers will be randomly generated. So as you can see, recall our equation, A sub x minus j modulo M, And in order to generate these random numbers, you must confine a, m, and x naught in order to receive remainders of this Euclidean division. So that is how multiplicative linear congruential generators work, and they're a little bit different than the mixed linear congruential generators and linear congruential generators in general. And the main difference is that this c equals 0, so it confines your variables a, m, and x naught. Here are the references that we used for this part of the presentation. Thanks for listening.